Okay, thank you for joining in. This is Larry Johnson with the Light Brigade, and we're holding a webinar today on fiber optic multiplexing technology. We're going to be covering a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. And if you have questions during the webcast, you can click on the Q&A widget and submit your question. We will try to answer these questions during the live Q&A portion at the end of the webcast. We're fortunate to have members of the Pinwell group monitoring the questions. So the questions regarding the presentation and the audio track, they will be answering online through the chat box, and those that are relative to the topic and the discussion, I'll hold those questions till the end of the session and address them as applicable. We have about 40 slides to present, so I'm looking at probably a 40-minute, 45-minute presentation followed by a Q&A section. So let us know if there's any problems in that. And in the meantime, let me go ahead and start the presentation itself, and I want to thank the Pinwell staff for coordinating this effort. Okay, and a little note on the housekeeping items and the website for the presentation materials, and again, the presentation box. Let's go ahead to the next slide here. A little background on the Light Brigade. I'm not going to read through this. I figure everybody can read themselves. But we have a lot of fun traveling worldwide, developing training programs. We're vendor neutral. Very fortunate. This is a very dynamic industry, and I wanted to lead off with this, that other transitions taking place. And for those that have been in fiber optics for some time, you may have participated in some of these transitions, and from the conception of the fiber optic industry, of course the theoretical years in the 50s and 60s, but in the 1970s, the first multi-mode fibers, up through the about 1983 time frame. And then in 1983, the single-mode fiber started to be deployed into the outside plant. That was a major transition, and one of the major ones in fiber optics. And the next major one occurred in the 1990s when dense wavelength division multiplexing occurred, along with all the technologies associated with it, which we're going to talk a lot about today, the component levels up to the system levels. And then in the 2000 time frame, we really saw the implementation of fiber driving deeper to the user, or fiber to the user, including both fiber to the home and fiber to the building. What is interesting is the fact that the components for fiber to the X came from the dense wavelength division multiplexing technology, period, and that we were just able to produce and utilize these, integrate them into systems at a much lower cost and so forth. And then we have another challenge, and that's what's occurring now, is that's solving bandwidth demands. So we're going to talk about the fiber limitations, the sources, passive devices, et cetera. So it's a unique time. We're in one of these transitions. It's very exciting. It's keeping the industry very busy. Lead times are going out on products, and every time we see the lead times go out, it tells us that there's tremendous growth occurring. Well, what's driving this is the transition, one case, from cell-based transmission to packet-based transmission, and this is really impacted by the Internet protocol in particular. And this means connecting data centers worldwide. And that anytime you're connecting data centers, then the effectiveness of the fiber, the latency or the speed or delays as well. And then the case of the fact that you may not have enough fibers for your needs, and that forces us to start addressing multiple wavelengths or optical multiplexing technologies. The other one is using the optical spectrum effectively, and so we're going to talk about the different ITU-specified bands and the different technologies and the different fibers associated with these and their limitations. And last but not least, the efficient use of bits. So how can we get more information per bit into the future? So that creates challenges for us, how to create innovative solutions capable of handling high-speed communication systems. And the tendency today is to really be addressing 100 gigabit plus. So we've had these transitions from what we consider legacy 10 gigabit systems, whether they're SONET SDH type, or in the case of the IEEE 802.3 Ethernet standard 10 gigabit Ethernet, to next generation systems from 100 gigabits literally into the terabit late technologies. And so the next generation systems must have lower latency, in other words, delays. So the speed of light is very critical in the speed of the system. We still depend on reliability. So for those that are attending that are in that have to address maintenance and restoration responsibilities, the fact is that a cable cut's a cable cut, and that we have to respond accordingly. And the higher the speeds are, the more that it makes it attractive to have alternate routing and optical switching and alternate paths for flexibility. And we need to be able to increase the scalability of the system. And at the same time, we expect to have a decreased cost per bit while using less power. However, we're limited by the legacy cables that are out there, the types of the fibers, their tolerances, and so forth. So first, I want to just give you a quick look at the fiber industry on 4 tiers. So the first tier is the component manufacturer. This would be a case of, say, a manufacturer that manufactures the laser diode. And then they would sell this or integrate it themselves into an optical subassembly. And then that tier would sell to the system manufacturer. And that tier would then sell to the service providers or the end users, and that who's going to implement it. Now, parallel to all 4 of these, there's very distinct testing requirements. A laser diode, the way it's tested, is totally different than what a service provider would look at as far as like bit error rate or eye pattern testing. And each of these different levels requires different types of test equipment, different criteria, and of course we depend on standards to define industry practices. So if we look at the basic wavelength division multiplexing system, we can multiplex 2 or more wavelengths together over a fiber, transmit it over a fiber at a distance, and then demultiplex that fiber. And the wavelengths are defined as lambdas. And fortunately, we have specifications that define what those wavelengths are going to be. So this takes place in the middle of this graphic that you're seeing. The graphic shows basically from a user input to a user output and what occurs at different levels, whether it's the electrical interface or the encoding or modulation of the signal, the actual light sources, which is where we go from an electrical to an optical interface. So most of the cases, these are laser diodes in different types, which we'll talk about. And then, of course, we couple that into the optical fiber, transmit it over a span, and then we reverse the process. However, in the case of wavelength division multiplexing, we have different wavelengths being assigned. So in other words, we have different lasers and different detectors and different components for each of the wavelengths, and we just happen to share them over the same optical fiber. So I want to look at the evolution of fiber optic systems, and if you start from the middle of this graphic and work out, it'll make a little more sense. So we started off with laser diodes, optical fibers, and photodiodes. That was our basic point-to-point system, and if we go back to the 1970s and through the 80s, this is virtually every system consisted of this technique. Then what happened in the DWDM years in the 1990s, we started getting a little more exotic. We started the development of pump diodes for optical amplifiers, and that we also found that when we had the optical amplifier that we could amplify multiple wavelengths simultaneously, and so that meant that we had to introduce optical filters into the receivers so that we could filter out the various wavelengths as well. And then take it one level beyond that, and you incorporate optical switches, and then you have management software that functions as well. And now we have more advanced modulation techniques on top of this. So we've seen literally 3 major evolutions of fiber optic systems, from basic point-to-point, optical amplification, optical multiplexing, and switching. So the next evolution is to take a look at what the standards bodies have implemented and why they implemented these. So the first one is this shows the 6 bands that the ITU specified as the G.692 standard. The first of these is actually the C band from 1530 nanometers to 1565 nanometers. This is specified because the optical amplifier, in this case the erbium-doped fiber amplifier, lased or amplified specifically in this region at that time this standard was developed. The shorter wavelength was then called the S band, the longer wavelength, the L band, and then we had the U band above the L band. And then we had to go backwards to the original band, which is our traditional 1310 nanometer center wavelength of the window or the spectrum. And then we filled it in later with the E band that filled between the O and the S. So we ended up with 6 bands. Now the case is that you have to marry the laser diode, the photodetector, and different amplifiers and fiber types to these different windows, and that's what we're going to show. So if you look at the ITU standards for different fibers and then the wavelengths that they are optimized for, the associated band, and then the purpose of these. So the first one in the O band is talking about the shorter wavelength, the 1310 center wavelength, is these would be standard point-to-point systems for the most part. Attenuation between about 0.25 and 0.4 dB per kilometer. It's not uncommon to use a semiconductor optical amplifier or SOA. And the fiber type that uses this spectrum the most is the ITU-T space G.652 and the low water peak G.652D fibers. And these are also, by the way, specified by the IEC 11801 standard as OS1 and OS2 fibers. However, in this discussion, I'm going to focus on the ITU designations versus the secondary IEC designations. The other wavelengths, as we go down here, as you can see in the different bands that different fibers are used. For example, when we start getting to the short band and the long band and the C band, these were optimized for the G.655 fiber, the non-zero dispersion shifted fiber, as well as the G.654 fiber, the ultra-low loss fiber with a much larger effective area. Now, there was also a reference to the U-band for future use, and just a statement on that real quick is the ITUs also specified the long and ultra bands to be used for maintenance and monitoring roles for future communication systems. Let's look at the G.652D fiber specifically, and the graphic shows this with a coarse wavelength division multiplexing chart showing several of the different channels. And out of these channels, you can see that the spectrum ranges from 1271 nanometers up to 1611 nanometers. Note that the cutoff wavelength on standard G.652 fiber is 1260 nanometers. So therefore, we're not covering below 1271. There's also, when we start talking about the E band, the wavelengths 1371 through 1431 should be used with G.652D fiber. This is a low water peak fiber, and on the graphic, you can see this at 1391, where the water peak in this fiber can be as great as 2 dB per kilometer of attenuation versus your standard 0.3 dB per kilometer wavelength as well. So here's a case where we can say specifically if I was going to use the E-band, then I really want to use the G.652D fiber so that I can reduce the attenuation level in the E-band. And these different channels on CWDM channels have been standardized so that we have a lower cost option for multiplexing signals, and we're using a much wider 20 nanometer channel than we would in dense wavelength division multiplexing, which we'll talk about soon. So CWDM is a choice, and we'll take a look now at the different fibers that are available and what their specification is and the nomenclatures for those. So the common single-mode fibers, all specified by the ITU. And the G.652 fiber, by the way, is an OS1 by IEC, and the G.652D is the OS2 fiber by the IEC. The G.653 fiber no longer exists, other than those that have been installed. It was not able to handle optical multiplexing without a nonlinear effect called four-wave mixing. And so it was obsoleted in favor of the G.654 cutoff shifted single-mode fiber and the G.655 non-zero dispersion shifted single-mode fibers. Later, the G.657 bend-insensitive fiber came out. This is actually a G.652 fiber. It has the same optical specifications, but it has several variations for bend-insensitive, bend radius, and so forth. So it's used a lot in optical subassemblies. It's used in fiber-to-the-home applications, fiber-to-the-building, etc. So the good news is we have standards here, and we're going to be utilizing these standards for different reasons. And the reason that we have different fibers is that if we consider the two basic fundamentals of optical fibers, and those are attenuation and dispersion, that each of these fibers has a different characteristic, and therefore we need to have standards established by those to address those issues. So the G.655 non-zero dispersion shifted fiber was designed for dense wavelength division multiplexing operation, which was really defined and specified due to the erbium dope fiber amplifier, or EDFA. It was originally designed for long-haul and oceanic spans, and especially in the case of oceanic, where a typical oceanic cable only has 6 fibers, so therefore we're not fiber-rich in any case, so we're really depending on time division multiplexing to go to the highest data rate possible with the laser diodes and electronics available, and then put as many of the different wavelengths or frequencies over the fiber as we can. And so DWDM with a G.655 fiber with an erbium dope fiber amplifier, it was a perfect marriage, the lowest attenuation possible, and so forth. And now, though, this fiber is also used by competitive local exchange carriers and many multiple service organizations. So note that this fiber is optimized for 1550, which is the lowest attenuation of all fibers in that band. But it's also dispersion optimized. So we have the minimal dispersion, and it's optimized for use in the fiber amplifiers. And we'll see if we can show a comparison on the animation here, so you can see between the two a G.652 standard fiber, and then we see a non-zero dispersion shifted fiber to where we're seeing some spreading of the signal, but that actually eliminates four-wave mixing problems. Okay. The G.654 fiber isn't as popular as the G.655, but it has its own benefits. It's a cutoff shifted fiber. It has a much larger mode field diameter than the G.652, and when we increase the mode field diameter, we increase also the effective area, which means more power can be coupled into this fiber. And for that reason, we can go longer distances, especially when we're dealing with optical amplifiers and long haul. So this fiber tends to be favored for oceanic and long haul spans, and that as well. Okay, and here we'll show another animation here, just showing the difference of the core size or the mode field diameter size between a G.652 and the effective area versus the larger effective area in a G.654 fiber. And therefore, the reason is much longer spans on a G.654. So if you're installing systems with hundreds of kilometers between locations, then you want the G.654 fiber. So we still have to deal with the active and passive devices that are going to be used in a multiplexing system. So the active devices are the network elements. They can be transmitters, receivers, in the case of fiber to the home, which I have some references to because there is some upcoming work in wavelength division multiplexing and fiber to the home network. So I introduced the optical line terminal and the optical network terminal here. as examples of this. Electrical optical switches are another example. Optical subassemblies where we can multiplex and filter different wavelengths bidirectionally over fiber. And of course, we go back to the basic components, the laser diodes and the photodiodes that are the part of every fiber system. But we also have the passive devices, and these could be the splitters themselves. They could be the wavelength division multiplexers, the filters, most likely Bragg filters, but they could be items like attenuators. They could also be wavelength lockers and other types of components as well. And remember that active devices always require power, and passive devices do not require power. So the first of these is the transmitter itself. We'll show an animation here. There's different types of transmitters. There's the Fabry-Perot laser. There's the distributed feedback laser. There's tunable versions. In this case, we're showing a laser with an external modulator, which allows us to transmit light at much higher speeds than a normal direct transmitted laser. Okay. The distributed feedback laser, in this case, will show an animation of a directly modulated laser. In other words, we're cycling the laser on and off by its modulation and its bias. At the same time, this type of laser is used for either analog or digital transmission. It's more expensive than, say, a Fabry-Perot laser. Typically used in data rates over 10 gigabits per second, but depending on its use, it may be at a lower rate. In case of fiber to the home, typically located at the service provider's hub, and definitely required for the 2 generations up on the wavelength division PON systems. Okay. Now, receivers, the opposite end, though, too, we still have to recover the optical signal. And different types of detectors, whether it's a positive intrinsic negative detector or an avalanche photodiode. And we can use a pin system on analog systems. They're lower cost, simpler. The APD, on the other case, is greater sensitivity, can much higher data rates, but it also has associated higher cost. Okay, so just a simple animation here. Again, we're just seeing a simple on-off keying on the laser diode transmitting to the photodiode, and of course the attenuation and dispersion occurs in the fiber, and then we have to compensate for that. So let's move on to optical amplifiers. And then once we can start covering the pieces, then we can start talking about how they're integrated together in multiplexing. So optical amplification occurs when the signal is strictly a loss of power of the original transmitted signal. And when we get to a certain point where we need to regenerate that signal, we have several choices to do so. In one case, we could go to a 3R function, retime, reshape, reamplification, which means back-to-back transmission equipment, or we use the optics themselves. And then there's 2 basic options available. There's the case of the erbium dope fiber amplifier using a rare earth fiber, erbium, and incorporated into the erbium dope fiber amplifier. And then the other one is using the optical fiber as part of the transmission itself, which would be used in Raman amplifiers. And one of the key benefits of optical amplifiers is they amplify multiple wavelengths simultaneously. So in this case, the erbium dope fiber amplifier, is the key. It's we thank Sir David Payne out of Southampton, England, for the development and the research, which also won him a Tyndall Award for his investigation research into the rare earth element erbium and to make the fiber, and Emmanuel de Severe out of France, who incorporated into the optical amplifier themselves. As David Payne told me, he goes, we're very fortunate that both the amplification range occurred at 1550 nanometers, but also that was the lowest attenuation on the fiber, and the fact that all these came together at one point, as even he said, was very fortunate and lucky. But EDFAs operate mostly in the conventional band. The G.655 fiber was designed specifically for use with the EDFA and for transmission of dense wavelength division multiplex systems. And the optical amplifier consists of multiple elements, and some of these you should be able to identify which ones are passive or which ones are not. For example, an optical isolator, which works as an optical valve, is a passive device. It allows light to pass through in one direction, but it filters the light in the opposite direction. It either eliminates it or minimizes it based on the specifications. The optical splitter or coupler is used to combine multiple signals together as well. So in this case, we see a pump laser, which would operate at either 980 nanometers or 1490 nanometers, and it would be combined at the coupler, a passive device. And then after it passes through the specialty fiber, the erbium fiber, then the pump laser would be killed off by the isolator along with any reflections that in the opposite direction. Okay. So this is the key type of optical amplifier and the one that's most broadly used. However, the implementation of Raman amplifiers is growing substantially, and these amplifiers use the fiber itself as the amplification medium, and it's based on the stimulated Raman scattering effects in that port. And they can be operated, unlike the EDFA, which is really closer to the C band and the short and the L bands, and the Raman can operate down into the original band, 1310 nanometers, and anywhere in between, based on the pump lasers that are used on these as well. So we'll show an animation of how these are used in both in bidirectional pumping, so that they're coupled to the fiber at both ends of the span, and you can see that the Raman as a downstream pump allows us to basically amplify the signal downstream, but at the same time you can have another pump laser amplifying upstream. So if you look at the red arrow, you'll see it's growing, and it continues to grow. In other words, amplify as it's being transmitted downstream. And when you start combining EDFAs and Raman amplifiers for extremely long spans, then we can start talking distances from hundreds to thousands of kilometers in a reach, in other words, oceanic and very much in the long haul. The other effect that you have with this is the increased power level. So all of a sudden we can go from a class 3 to a class 4 laser. So the automatic power shutdown and automatic power reduction features built into the systems is very critical. It also, though, means that lossy splices, contaminated connectors, they may need to be repaired or respliced because of the power levels and the disruptions they would cause. Also means you can't have macro bends on fibers or cable. You can actually have thermal heating occur on the jumpers themselves. So let's look at fiber optic passive devices. So these are the other element that are used in these systems, and they provide optical to optical functions. Some of the types are mentioned here: attenuators, splitters, wavelength independent couplers are used extensively in fiber to the home. So in other words, they have the same characteristics upstream, downstream, and at different wavelengths. So passive devices will be used to multiplex and demultiplex the signals. In other words, we have to filter wavelengths, we have to block wavelengths. We can also incorporate them into optical switches where we can switch fibers or wavelengths themselves. A little tiny break there, so I took a drink of water. Okay, so in the filters and gratings, one of the key elements is the fact that the fiber Bragg grating is used for optical multiplexing and demultiplexing of optical signals. We'll show a video next that shows how this works, and I'll just explain over the text as well. So the fibers could be standard fibers, or they could be a specialty fiber. But we have our input signal, and the Bragg gratings are designed to filter specific wavelengths. So when we match up to the ITU grids on dense wavelength division multiplexing, or say even coarse wavelength division multiplexing or so, we can be very specific whether it's a 50 gigahertz spectrum or a 20 nanometer spectrum being demultiplexed. So these are passive devices. They can also be used for dispersion compensating, and the benefit they have on dispersion compensating versus the dispersion compensating fiber is they don't have the latency issue or the attenuation issue that a DCF would have versus a Bragg grating. So let's look at some of the different multiplexing options now that we've seen some of the elements that are involved with the system itself. So the traditional wavelength division multiplexing was the dual wavelength, 1310 and 1550 nanometer, wide WDM in essence. And then there's variations of these from coarse wavelength division multiplexing and dense wavelength division multiplexing. As you notice, as the spectrum's going to get tighter, then the type of laser is affected because of the spectral width of the laser. So the lower cost Fabry-Perot laser couldn't be used in a DWDM system, where we could use it in the broader coarse wavelength division multiplexing system. So let's take a look at each one of these. So the wide WDM is an actual G.671 specified standard that says that each of these wavelengths has to be at least 50 nanometers apart. An example of a wide WDM is on fiber to the home, where the G.983 broadband standard defined the upstream and downstream wavelengths on fiber to the home. And in this case, the 1310 for upstream transmission, 1490 for downstream communications, and the 1550 nanometers used for RF overlay functions. They're all spaced 50 nanometers apart, greater than 50 nanometers, so it would qualify as a wide WDM system. And and again, this is based from center wavelength. We still have to deal with peak power levels of these, and then we measure these lasers at full width at half max, so in other words, 3 dB down from peak power, and then the spectrum across. The next standard is the CWDM standard, and I'm doing these from simplicity to complexity, not historically, because DWDM was the first system, then coarse wavelength division multiplexing was the second, and wide, and so forth. So in this case, the CWDM standard is specified by the G.694 standard. It's based on 20 nanometer channels. It really is optimized for the low water peak G.652D single mode fiber. And again, as I noted before, we really want to pay attention to the OH peak in the E-band when using legacy G.652 fiber. So I'm going to take a little tangent here, and what does this mean? For any of the carriers that are here, that are listening in, if you installed standard single-mode fiber from 1983 all the way up through about 5-10 years ago, the odds are is you have G.652 fiber, and it also means that you have a high water peak in the E-band here. And it hasn't been a problem for you because you've transmitted it either 1310 or 1550 nanometer. But in the future, should you decide that you due to fiber exhaust, that you want to open up the spectrum and use CWDM, you would notice that you would have a huge attenuation penalty at certain wavelengths in that, and these would occur between historically about 1371 to about 1411 nanometers. So the only way to know if you haven't documented this fiber or what type of fibers in your plant, which, by the way, you should always do, not by the cable manufacturer, but by the fiber manufacturer and the specific fiber that's in that cable. Most likely you have this water peak in the E-band, and therefore I would stay away from those channels where that exists. Or next time you're buying an OTDR, take a look at one that can have a tunable laser in it, or get a CWDM OTDR so that you can actually test channel by channel versus your conventional OTDR. So let's go on to the next slide, okay? And take a look at DWDM. So this is specified by the G.692 standard, and there's 3 variations on the spectrum. The original 200 gigahertz channel spacing, which equals 1.6 nanometers in width, the 100 gigahertz spacing at 0.8 nanometers, and the 50 gigahertz and 0.4 nanometer spacing, of which the 100 gigahertz is the most popular. 50, there's a cost penalty just because the optics and the electro-optics are going to be more expensive. And we've seen other products manufactured, but not necessarily in the standard, the 25 and the 12.5 gigahertz standards. Okay. So now what's interesting, though, is the next generation of fiber to the home, called WDM PON, uses basic WDM, as I explained before. It uses wide WDM with a 50 nanometer spacing, but if we go down below, we start matching the wavelength, the spectrum that's assigned, with the functions and also with the different bands. And then each of the standards that have evolved have come up with new ones. And an example of this is the next generation PON 2, otherwise known as the WDM PON. This is specified by the ITU's G.989 standard. And in this case, if you're putting fiber to the home, installing it today or considering it, you're actually in several evolutions. The legacy PON, which could have been the original G.983B PON standard, the IEEE 802.3 EPON standard, or the ITU's G.984 GPON standard. Those are all legacy standards using G.652 fiber. Well, what happens is that as your bandwidth needs go up, you don't want to replace that physical plant. So what you want to do is go to a next generation, and then the next generation is actually the 10 gigabit PON, whether it's the EPON, 10 gigabit EPON by the IEEE or 10 gigabit GPON by the ITU. All you're doing in this case is you're increasing the data rate from about a 2.5 gigabit to a 10 gigabit level, and so you're getting a 400% growth in your available bandwidth, but it's not a tremendous increase. Now, but it is your next transition or migration plan. After that, your next one is to go to WDM PON, which allows 8 wavelengths using the DWDM spectrum, and these will use the spectrum from 1596 nanometers to 1603 nanometers downstream using 100 gigahertz spacing. So then you get a choice of what's on screen now. In other words, if you take a look at this, you have a choice of the power split or the wavelength split. If you're using the existing splitters that are in your legacy and 10G PON systems, you don't have to do anything at the splitter location, but we're going to be depending on the optical network terminal to have tunable optics and to be spectrum specific, or to be spectrum specific. Most likely to be tunable optics on the side, so it'd be easier to activate and manage. So that's overlay and a legacy system. The other option would be for, say, greenfield applications where you want the filter to replace the optical splitter at the cabinet. In this case, we can eliminate, say, 15.8 dB on a 1x32 splitter, and we use the 1 dB for the wavelength splitter instead. So what that gives us is much lower attenuation. That could be used two ways, either lower cost electro-optics on the OLT-ONT side, or we can go to extended reach function. So instead of being limited to 20 kilometers, that we could go up to 60 kilometers per the standard. The other thing we get is we can dedicate wavelengths specifically to users. So just like active Ethernet is a dedicated fiber from the service provider to the end user, in this case, you would get a dedicated wavelength that would be assigned, and that, again, it would be using the 100 gigahertz spectrum. Then we'd be using TDM, time division multiplexing to get to the highest data rate that you want. You could also have a combination so that you could put say an 8 wavelength system out and then put a splitter at the end, so you can have a coexistence with both wavelength and splitting capabilities. Okay, so let's take a look at some of the common components that are available, and these consist of some basic components such as couplers or attenuators. I found these in one of my little buckets that I keep, and if you notice, they say 1,300 nanometers on them, if you can read that closely. It actually tells me that these are from the early 1980s versus the late, because the term that we use today is 1310 nanometers for single mode didn't get used till 1987, so the first 4 years of single mode was 1,300 nanometers, not 1310. And that just happened to be the best. 1308 was the best wavelength for optical transmission to oceanic, and which we found in 1987. So anyway, how the 1310 term came around versus the 1300 nanometer term still used by the multi-mode industry. So anyway, common elements or components can be from the basic laser diode themselves, modulators, external modulators, the pump lasers that are used in these systems, different types of photodiodes on receivers with different spectrum for receiving indium gas germanium, indium gallium arsenide phosphide, for example, germanium types. Different types of filters, whether they're Bragg filters or bulk optics. Different types of couplers or splitters, such as the fused biconical taper or the planar types, optical isolators, optical circulators, and when you combine a circulator with a Bragg filter, you can have optical add-drop multiplexing, and in the case at the bottom, whether reconfigurable optical add-drop multiplexing, where we can combine different components to get different phenomena to occur. Optical attenuators from a very basic component, basically bulk optics, and then dispersion compensators as well. Now, if we look at this on a grid system and look at each of the elements on a DWDM system, you get an idea the breadth of the optical industry from a component to a system level and how different components are being integrated together to create a optical multiplexing system. So we depend on a lot of technology, and we depend on that four-tier structure. Remember very early in the presentation where we talked about optical components to optical subassemblies to optical systems to the system, the service provider. And in this case, the service provider would never see these elements, and even at the system manufacturer, they're integrating the components together. And even today, one of the neat things is new technologies such as photonic integrated circuits or PIC technologies, to where multiple levels of these are being integrated together at board levels to eliminate connections and failure mechanisms together. And so it's a tremendous industry. And again, remember that this chart doesn't say what the wavelength is, and it doesn't say what the fiber is, and but all those have to be married together. Okay? And so this next chart just kind of gives a kind of an overview of the industry over the decades, is saying that the capability of the network keeps increasing substantially. The economics as both a CapEx and OpEx issue is still there. The price per bit decreases continuously. We're using optical multiplexing to resolve problems, mainly fiber exhaust and so forth. The fiber industry is growing very healthy, and we're going to be incorporating more route redundancy and more optical switching technologies, a lot of reconfigurable optical add-drop multiplexing capabilities. And the key elements of reliability, functionality, and management issues still have to be addressed. So, as a summary, there's multiple variations of WDM. WDM provides a cost-effective solution for fiber exhaust. Fiber exhaust means that we didn't put in enough fibers at the time, or the demand is up so much that we need to have more solutions, so we're going to use multiplexing eventually. We'll use time division multiplexing as high as we can, but eventually we're forced to go to optical multiplexing. And anytime we go to a tighter spectrum, it ends up being more expensive. So DWDM is going to be less expensive than DWDM because of the detail of the specifications and the types of products, in other words, components that are used. And again, attention to details for active and passive devices. We're really looking at those four tiers. The reason that there's different test requirements and different types of equipment for each one of those tiers is the fact that we have very exact specifications to follow, and system manufacturers who are developing high-end transmission systems pay a tremendous amount of attention to their components and their optical subassemblies that they're incorporating and integrating into their systems. And the ITU's done a great job of defining and specifying optical fiber types for the system service providers that are here, that are participating. I can't stress enough how important it is for you to characterize your optical fibers, to know the fiber that you have installed, the manufacturer, the exact fiber and its characteristics for dispersion in particular, and that for high-speed systems. And that the testing, keep in mind that the testing and test equipment have evolved and will continue to evolve to address the needs of optical multiplexing, and including optical spectrum analyzers, wavelength division multiplexing and products, tunable OTDRs, wavelength meters. Also keep in mind that just the basic cleanliness of a connector can affect any of these systems, so we can't forget the importance of cleanliness here. And I've used content in this presentation from several of our DVDs that we produce. The part numbers are on here. There's different chapters. We have PDFs on all of them on our website, and we'll give you that in a second. But unfortunately, in 45 minutes, you really aren't able to spend as much time as you want. But one of these typical DVDs is about an hour and a half divided by how many chapters. So there's a lot more information on these that I could provide in this time frame. And, of course, the animations came from here in the explanation. So, we just give our contact information, and then I want to start moving on to the questions here and see what we can address here. So let's take a look at the question pool. Okay, let's see. As far as the future trends, question on future trends here. What we're going to see is some different technologies, and the high-speed systems on the 100 gigabits and up. If you go from different data rates to different formats, then the modulation schemes have to change. And our simple on-off keying that we've used in the past, in other words, turn the laser on, turn it off, whether it's directly modulated or externally modulated. Those systems are still effective to 10 gigabits and all, but virtually at 40 gigabits and 100 gigabit systems, we're using advanced modulation schemes, and to get more information per bit, and that, in other words, using the spectrum. And we cover this in our high-speed DVD, where we talk about the different type of constellations, the importance of the eye pattern. And if you take a look at this from whether you're a service provider or a system manufacturer, the testing requirements are going to change to address these higher speeds as well. So do pay attention to them. Let me go to another question here. Okay, what's the effect of PMD at 100 gigabits? And so one thing, polarization mode dispersion has been a limitation, and when we migrated from 10 gigabits, virtually all fibers, we were advising to characterize these for chromatic dispersion and polarization mode dispersion, PMD. And so what happens is this chromatic dispersion, no matter what data rate, is still going to be there. But there's ways we can mitigate chromatic dispersion through Bragg grating technology, or we can use dispersion compensating fiber. So there's a couple solutions. The systems manufacturers, though, are going to require for them to optimize the transmission system to your plant, they really need to know the attenuation level, the optical return loss level. Of course, that's affected by the reflectance of any component in the system, and then the PMD values. However, with the newer high-speed systems, the use of forward error correction and coherent detection is mitigating a lot of these problems. So we're not seeing as much of an issue with PMD at 100 gigabits than we are at 40. But it is still a factor, and it needs to be addressed. And again, we have a couple different DVDs that address PMD and CD effects. Okay, and let's see. The case of other future trends, what is multi-core fibers? And that multi-core fibers are a new type of fiber that has literally within the same geometry, 125 micron OD, is multiple cores, and one common number is 7 cores in a fiber. So if you think about this, it's a new type of fiber. It's been around for about 10, 15 years. Most of the specialty fiber manufacturers are manufacturing it, but the difference is they're typically manufacturing in smaller spans. So it is a technology to pay attention to, and with that technology, my thoughts are, and that is saying, how are we going to splice it? Now, we do have fusion splicers with rotation stages, so this isn't new to the industry. So we can, but the tolerances of the actual multiple cores in the fiber are going to have to be addressed. The other one is, how are we going to fan these multiple cores out at the end of a fiber? So if you look at it just like a fiber with a cable with 7 fibers, think of it with a fiber with 7 cores, but now you have to line up with each one of those cores and then be able to drop a fiber off and line it up with the transmitter or the receiver. And so some type, I imagine this is going to be handled through some type of filters, gratings, or bulk optics. We'll see. But it's an interesting technology, and it's one that we're going to see more into the future. The other issue is at the middle of fiber spans, like now we can do a mid-entry. How would we do that with a multi-core fiber and that? So there's a lot of physical layer topics that need to be addressed here. Okay, so there's some questions that I am not able to get to at this point, but I will respond to directly with each of you. I really appreciate you sitting in and taking the time today, and we look forward to our next presentation in September, and we're going to I'm giving great thought to talking about technician disciplines in the advanced technology systems, and that as a subject. But if anybody wants a specific subject, I'm open to suggestions. We're going to be providing these every 2 months for the next few years, so we're really looking forward to getting back in front of everybody and addressing their different topics. And at the same time, we'd like to thank the Pinwell Group and the staff. And this presentation will be archived within 24 hours and can be accessed from the homepage at www.com. Reminder, email, message for the archive will be sent to all registrants, complete with a direct link to the archive. So we want to thank you for joining us today. And I believe I just gave the wrong email or web address. I think it's www.lightwaveonline.com. And that. So sorry, sometimes you have faux pas. And if you have a question directly, my email address is larry@lightbrigade.com. And I look forward to hearing from you and having you participate in a future webinar. Thank you very much.